Okay, so now I would like to welcome our next speaker, Dr. Alamgir Hossain from Department of Mathematics, Ashoka University, Haryana, India. So the title of his talk is Fractal Approximation on the Real Projective Plane. So over to you, Alamgir. Hello.
Okay. Hello. Thank you. Thank you, Olga, for introducing. Can you hear me?
Yes, yes.
Yes. Okay. Thank you. A very good morning, good afternoon, and good evening to all of you. So my name is Alumgir Hossain, and today I give the talk on fractal approximation on the real projective plane. So first of all, what is the motivation of that work? So we know that in real life there are many geometric objects that we can't approximate by the well-known fractal function or fractal approximation like that we have defined in Euclidean space. For example, if you consider the symmetric cone in R3, then there is no traditional to approximate that function by a fractal function. So for this regarding, we are we have tried to define some function that may be approximate that type of geometric object. So it's maybe don't know why. Okay. So first of all, we have already actually this is you can think the continuation of the of our previous work that already the Professor Nasim Akhtar is presented. So here just I recall that the RP2 is already we have seen that this is the collection of all lines which is passing through the origin, and the class element of this space is defined by denoted by like this. And we all already we have seen that the hyperplane in that space is that H is all those points where Q is perpendicular to P. So here P is the normal of that hyperplane. And we have already seen that any element of RP2 minus E3 here is it the hyperplane, which is actually nothing but the XY plane, the line passing through the XY plane. And we can express these two elements. So that is the space can be expressed as like this. Here we use the different notations, H and K, where H is the those class element where Y coordinate is 0 and K is the those element where X coordinate is 0. And we all have already seen that the projective interval, if we consider two elements which is strictly less than and each other, then the positive interval which is denoted by pi0 and that is the positive interval. And as script C of pi, the collection of all continuous functions. And this space becomes the complete nonlinear space with respect to the subnorm that we have already seen. Now we are discuss about projective polynomial approximation on the projective interval. So first of all, we define the projective polynomial. Here we consider the polynomial Pn from H to K, which is defined like this: n x to the power n and a0 z to the power n clone zn, where ai are all real and an not equal to 0. And also, if we manipulate or we calculate this value, Pn lambda x 0 lambda z, where lambda not equal to 0, then this is equal to Pn x 0 z. for the projective, we know that this is the class element. So the class is multiplied by lambda. This is give the similar class. So this is for this reason, these polynomials are well defined and that space. And let Pn script Pn is the set of all projective polynomials of degree less than or equal to n. And script Ps is the collection of all those polynomials. So first we have this proof that theorem that Stone's-Weierstrass theorem on projective interval. If Pi is the projective interval within the interval whose beginning point is 0, 0, 1 and end point is 1, 0, 1, then and f is any continuous function, then there exists a sequence of projective polynomial Pn such that Pn converges to f uniformly. And we know that any interval, if we consider the in arbitrary interval, then these two intervals are homeomorphism to each other. So we can define any function from any interval, and then we can approximate that function by the projective polynomial. Now we have seen the construction of non-affine fractal function. Here we consider the data point xn, yn, zn, and that satisfy the partition conditions. And with slight abuse of notation, we have already seen that xn, yn, zn can be written at that like this. And let pi the projective interval, and pin times 0 is the sub-interval of that projective interval. So here we actually first interval is considered from x0, 0 to z0 to x capital N, 0, z capital N, and this is the sub-interval xn minus 1, zn minus 1 to xn to z. And ln, here we define ln from projective interval to the sub-interval, the contractive homeomorphisms that maps are given by like this, where this ln satisfy the join-up condition. And let g be any continuous function that interpolate the data points. And consider the continuous function fn from you can say we can think about this is the product of projective interval and the space k to k like this, where alpha n and dot product, we have already seen that this dot is defined by some rules, and that b, here b is a continuous function that satisfies this two relation, and with b not equal to g. Now we define the map wn, where wn is the sum of the map ln x0 z and fn xyz. Then this form a iterated function system, and this collection is called the real positive iterative function system. And we have already seen that if the alpha n is satisfy the condition, the mod of alpha n is strictly less than 1, then this IFS becomes the hyperbolic, so or contractive. So we have already previously we have seen that this IFS has an attractor, and this attractor is denoted by G. Now our claim is that G is nothing but a graph of some continuous function. So here we define as script C is all those continuous functions that satisfy these two conditions. And then this script C is the closed subset of the complete matrix space. So this is complete also. And we define the real positive Redd-Bashirac-Trevik operator. So notation is RPRV, which is defined like this: Fn L inverse of this plus Fn compose L inverse of this, where Ln inverse is given by like this. Then we have proved that this operator RPRV operator T is well defined and contractive on the complete matrix space. or complete non-linear space. Hence, by Banach fixed point theorem, T has an unit fixed point, which is denoted by G alpha in C, and G alpha is now known as a non-affine real positive fractal function, or RPFF. And we have proved that this graph of that function G alpha is nothing but the attractor of the corresponding real positive iterator function system. Here we have seen an example. G of x0z is equal to 0 x squared z squared. This is our classical function, and this is our corresponding non-affine fractal function that approximates our classical function. Now, projective fractal uniform approximation. We have seen that if we consider any continuous function from the space of continuous function on the real positive interval, then we can approximate that function by a fractal version of that function. So similarly, if P is the polynomial that satisfies some certain condition, then P can also, we have approximate that P by some fractal function, which is denoted by PL. And then we have seen that theorem, that fractal version of Stone-Weierstrass theorem. If f is any continuous function and epsilon is positive, and delta p is the partition of the interval pi, and if L is the function from the continuous space to continuous space, which is not equal to identity, and satisfy those two conditions. So here we consider L instead of B. So we know that the B is the function that satisfies some condition. So similarly, here we consider the function L, which is bounded linear operator. And under that condition, there exists a fractal projective polynomials P naught alpha with P infinity is maximum of P n that is not equal to 0. And then we can approximate the function f by that projective fractal polynomial. So we can say that that function can be approximate uniformly by the fractal version of projective polynomial. Now the dual of non-affine real positive fractal function. This is the most crucial part in this article, and this part is interesting for me because this is the dual. Actually, dual is not another type of space. We know that for the real Euclidean space, the dual is the collection of the functional, and also we know that the kernel of that functional is the from a hyperplanes. So here we have seen that some different thing from the traditional our fractal function in positive space. So here we dual non-affine real positive fractal function. Here we consider the RP2 with a collection of all hyperplanes of the positive space. Or equivalently, we consider the all hyperplane P par. Here P par is those hyperplane where P is the normal of that hyperplane. So this is the dual space. We are taking only 3 hyperplane, but this is not a collection of 3. This is uncountably many hyperplane, which is passes through the origin of that space. Now here we consider the dual space, in particular RP2 minus HE3 corresponding the dual space this, and we induce the addition on that dual space is like this: P par plus Q par is nothing but a P plus Q par. So here P par and Q par is the two hyperplane, and this is we use the same notation, but this is different from that notation actually. Actually, we know that already we have defined this plus circle is in our projective space. So this is the P plus Q, and we take the corresponding hyperplane. And we define a dual metric. This is denoted by dp hat. Is p par q par is nothing but a distance of the normal of that two hyperplane P. Actually, P and Q the normal, so we consider the corresponding distance of that two normal on that space. And we consider the map Q from the real positive space to the dual space given by Q of P is P is equal to P par, which is called the duality map. And this is the remark that then this space RP2 minus with respect to the positive metric and the dual space with respect to the dual metric are isometrically isomorphic, and Q is the corresponding isometric. And hence, this dual space with respect to the dual metric is become a complete metric space. Now let we consider the collection of that hyperplane, which is denoted by H hat, is the image of the hyperplane H. That is, we consider the hyperplane X bar, where X belongs to the H. And K hat is the image of K with respect to Q. So this is actually we consider those hyperplane where Y belongs to K. And now we know that already if X is any element, then X can be written as X1 plus X2. This is actually we call it plus, but this is not usual plus. So, and if we consider the parp of that element, then this is actually whole parp. So here we consider X parp is equal to actually X1 plus X2 the whole parp. And we already have defined that on the dual space, this parp is equal to nothing but a X1 parp plus X2 parp. So in this regarding, this space RP2 minus H3 hat can be expressed as a sum of that two, or we can say that direct sum of that two space. Now we consider the data set Pn on the space RP2 minus HE3, where Pn is the collection of that hyperplane where Xn, Yn, Zn are given already given as above. So this is our given data point, and then we consider the corresponding hyperplane Pn. Now, any Pn also can be written as say Hn plus Kn, where Hn is the corresponding that hyperplane where y coordinate is 0 and Kn is the collection of that hyperplane where x coordinate is 0. And we consider the dual projective interval. This is actually nothing but the image of the projective interval, and the dual sub-interval is the image of that projective sub-interval. And then we define two map, ln hat and fn hat. This ln hat is the where we consider the dual hyperplane x0z, actually nothing but the hyperplane of that image of that point. If you consider the image ln x0z, and then we take the corresponding hyperplane. So this is, we have defined like this. And similarly, in similar fashion, we define the fn hat is the hyperplane, which is where fn x, yz is the normal to that hyperplane. Where ln fn are given, already we have defined that ln fn for non-affine case. And also wn defined like this by we just taking the addition on that dual space. And after some, so then this collection forms an IFS on that dual space. And we are called this space dual real positive iterative function systems. And after some manipulation, we can see that this Wn can be written as the original, if we consider the original Wn x0z, and if we consider the corresponding hyperplane, then this is equal to that. So this Wn can be written like this. Hence, it is easy to say that Wn hat is satisfy the join-up condition. And also, this Wn is satisfy, actually this map are isometric with respect to the dual metric. So hence, So if we already know that if alpha n belongs to the -1 to 1, then our original IFS real positive iterative function system is contractive. And from this relation, we have seen that this Wn had also the contractive with respect to the dual metric. Hence, this IFS has an unique fixed point, which is we denoted by G hat. Now we have proved that theorem. This theorem is, you can think about that already we have proved, we have seen in the Euclidean space or some nonlinear space that if there exists some, so we can prove that if there exists a function z hat that interpolate the data points and the graph of z hat, sorry, this is the typo, this is actually z hat. So graph of g hat is equal to capital G of hat. Now this is complete that theorem, but there is some more extension that moreover we have seen that the graph of G hat is the collection of that hyperplane where P is belong to the our original function G alpha. P belongs to the graph of that function. That is G hat is nothing but a collection of that hyperplane where P belongs to the our original attractor G. So here we have seen a example. This is our actually classical dual function. If uh, graph of that classical dual function, and this is the corresponding dual non-affine real positive fractal function. And you can notice that this function, this is actually collection some hyperplane. So this is passing through the original that plane. And you have seen that this is the smoothness of that plane, but there is some peak point here. Here you can see that there is some peak point. So this is not a smooth space. So it is depend on the scaling vector. So here we give some reference. The first, this is the written by the Barnsley positive real positive iterative function system, which is in 2012, and some reference on the positive geometry. And this is our earlier article, which is I am written with my guide, Dr. Nasim Akhtar and Professor Navas Kasman, fractal interpolation function on the real positive plan. And this is this is the that article that I present here. So this is the fractal approximation on the real positive plane, which is published in electronic transaction on numerical analysis in 2026. Thank you. So if you have any question, you can ask.
Thank you, Alamgir. That was a nice presentation. So now I would like to request to the audience if they have any question to the speaker. Okay. So if not, thank you again. So for the next talk, we'll have in 1 to 2 minutes. Okay.